Okay, welcome back to the session that we're now doing on the interesting question of the difference between natural and forced, or natural and anthropogenic variability. We have two talks in this session, and our first talk is by Professor Tim Palmer of the University of Oxford and of this academy, who will be telling us about climate predictability. And Professor Palmer has a long history of very interesting and provocative works on the general question of weather and climate predictability. So, Tim, I'm going to interrupt you 5 minutes before the end of your talk, that is 25 minutes from now, just to tell you that you have 5 minutes. Take it away.
Okay, thank you, Kerry. And let me just share my screen. Yes. Let me just, okay. So, Kerry, can you hear me and can you see that?
Yes, indeed, Tim, go ahead.
Okay, so Kerry, I'm going to address the theme that you talked about, but I really want to talk about it in the context of I think the first of the COP recommendations from the Academy, which is of the need really to up our game in simulating and predicting climate. So the background is one of the famous Atlas detectors at CERN, the Large Hadron Collider, and I want to argue for something like this or at CERN at least, for climate change. Yeah, just to start by saying, of course, in meteorology and climatology, we have and we use very successfully, I think, a hierarchy of models from simple to complex. The simple ones to inform our understanding of the climate system, and the complex ones to make predictions and projections which become policy or are policy, hopefully are policy relevant. So a very simple example is the Lorentz Model, which of course Ed Lorentz used to show that the atmosphere is unlikely to be periodic. It's unlikely to repeat itself in a cyclical way. And that makes statistical long-range prediction problematic. And that was quite clearly demonstrated in his very iconic model of chaos. And then at the complex end, we try to solve the exact nonlinear partial differential equations of climate as accurately as we can. These unpack into many, potentially trillions of individual equations, and we need the biggest supercomputers to try to solve them. Oops, let me just, sorry. Okay, just very briefly, I want to give one example of work I did a long time ago with the Lorentz model as sort of example of how these models can be relevant to our thinking. The diagram on the right there shows, so if you remember, the Lorentz attractor had those two lobes, looks like a butterfly. The two lobes can be thought of as regimes, quasi-stationary regimes. And what I'm showing here is 4 pictures of these two regimes plotted as probability distributions in 2 of the 3 dimensions of state space, the x and the y direction. So the regimes are kind of blobs of high probability, roughly along the x equals y diagonal. But in this model, what I've done is to add an extra term to the equations. Whoops, sorry, that's a mistake there. At the top there, add an extra forcing term to the x and the y equations to sort of simulate climate change in a very, very crude way as a kind of an external forcing. And the non-linearity of the model shows up in the fact that the regimes themselves actually don't change. The forcing doesn't change the position of the regimes in state space, but what happens is one or other of the regimes becomes more likely. So that the 4 figures just show 4 different directions in phase space for this forcing term, f cos theta, f sine theta. And what you see really is that the response is actually relatively insensitive to the forcing for a range of angles. And what really, as I say, manifests is that the probability of the regime, or one regime or the other, becomes more or less likely. So if we think the atmosphere has regimes, and as I will show shortly it does, then it's really, if this model is relevant at all, it's telling us it's really quite vital that we model these regimes accurately if we want to know what the weather is going to be like at a particular place. A regime in the real atmosphere could be something like a blocking anticyclone, or something like the North Atlantic Oscillation, something sort of large-scale quasi-stationary weather pattern. And indeed, this sort of model can explain quite simply, I think, how it's not paradoxical that regionally we could actually expect climate change to increase the likelihood of spells of cold weather. And this was actually brought out very recently in a paper only about a week ago by Judah Cohen and co-authors, suggesting that the very cold weather that was experienced in Texas, which led to all of their electricity grid shutting down in February of this year, could actually be a consequence of climate change. So, you know, a model like this can explain that in general terms, but it also makes the point that it's crucially important to get these regimes correct. But now let's turn to the other side of the hierarchy, because, you know, this year we've experienced some extraordinary weather events, and we wouldn't obviously expect a Lorentz model or anything like it to be able to simulate these extreme events, but we would expect our most complex models to do a reasonable job. So this is a picture of the wildfires in British Columbia during the period where they experienced almost 50 degrees Celsius temperature. This is just a couple suffering from the aftermath of the flooding in the Rhineland. And from this CNN article, Michael Mann, that I think you, Kerry, mentioned yesterday, made the comment that the signal of climate change seems to be emerging from the noise more quickly than the models predicted. The signal is now large enough that we can see it in the daily weather, even though the models didn't see it coming. So was Michael right to say that? Well, since that article, which was in July, we've had some more events. We've had flooding in Henan province in China. These are people in a subway train. The Chinese said this was a once in a 1,000-year event. And then even more recently, the flooding in New York. And again, the subway train in New York. So, you know, these events also were not predicted or simulated, not even predicted, not simulated by the models. They're completely out of the range of current generation models. And in fact, even the forecasts of this event were not terribly good. And Cliff Mass, one of the leading meteorologists in the US, in his blog, wrote this, that everyone involved in numerical weather prediction knows what this country needs to get such forecasts correct. A relatively large 30 to 50 member high resolution, 3 kilometers, just remember that number, 3 kilometers, for grid spacing, ensemble of forecasts that are carefully calibrated. Okay, so all of these events are in fact completely out of the range of the current generation of climate models. And as I mentioned yesterday in one of my questions, it makes it actually impossible to do any quantitative attribution of these events to climate change, because the probability of them occurring in a model, whether it has pre-industrial or current CO2 levels, is 0. So your attribution ratio is 0 divided by 0. And this was an article from this morning's, I'm right up to date now, this is this morning's independent newspaper in the UK, which actually just makes the point that we've had enormous media coverage of these events in the US and Europe and in China. But in fact, at the same time, Africa has also been suffering enormous droughts and floods and heat waves and fires. So, you know, we are really talking about global problems here, not just regional ones, and the media often fails to report some of these events in other parts of the world. Okay, so why are the current generation of models not doing a good job, or in fact doing a completely lousy job at simulating these events? Why are they completely out of range of the climate models. And to understand that, we have to kind of go back to how we actually solve equations like the Navier-Stokes equation, which, along with the thermodynamic and continuity equations, are the bedrock of climate models. And of course, we have to unpack this into a series of ordinary differential equations, or in fact, ordinary finite difference equations, by projecting onto some grid spacing, some grid boxes with a finite spacing. And then we try to represent all the processes like clouds or flow over small scale mountains or radiation from the sun or infrared back to space with parameterizations and indeed turbulence in the boundary layer. And I should also say, of course, and also the effects which can't be resolved in the oceans, which are a lot of the mesoscale eddies, which we see in places like the Gulf Stream and the Kuroshio. And a parameterization is a formula. You input the variables from the dynamical core, and you might have some free parameters. And the parameterizations try to tell you what the clouds and the turbulence and the flow over the mountains are doing at a particular grid box and a particular time step. And a lot of work over the decades has been trying to find the best parameterizations, the best formulae. But as anyone who really knows the Navier-Stokes equations well, and here I would particularly note our president, Professor Parisi, who's an expert on this more than anyone in the world, because of the properties of this equation, in particular what's called the scale invariant properties of these equations, there actually is no such formula. It's a forlorn hope to assume that such a formula exists. There is no formula. All we can do is somehow approximate as best we can, but ultimately there is no formula. It's a holy grail that doesn't exist. There is no formula. So we are making inherent errors when we try to fit these subgrid processes with a formula. I myself, for a long time, have been trying to persuade the community to treat these as actually stochastic in nature, to add noise to represent the fact that there is no formula. And the problem comes that when we look at our climate models, the CMIT models, a typical grid spacing is around 150 kilometers. Remember the cliff mass of 3 kilometers. We're a long way from that. We're 150 kilometers. So we're nowhere near being able to resolve the types of thunderstorm clouds that Kerry, you talked about, and that were so critically important for a lot of these events that we're talking about. So we do need order, let's say order a kilometer. It doesn't have to be precisely a kilometer, but order a kilometer to resolve the storms that flooded New York, Henan, Rhine Valley, and so on. And once we can do that, we can then get rid of the parameterizations for things like deep convection, or in fact the flows over, or the production of gravity waves by small scale topography, or the parameterization of these ocean mesoscale eddies. But there's a problem, because this will require at least exascale computing, which means 10 to the 18 floating point calculations per second. Now, okay, you may say, look, okay, this is all very well, but maybe we're not so much interested in these particular extreme events, as long as we can get the large scale climate response to CO2 correct. So I will argue that actually the models can't even do that. And to illustrate that, this is a figure from a paper by myself and Bjorn Stevens, who's director of the Max Planck Institute in Hamburg. We took 3 of the leading climate models, the Met Office, NCAR, and Max Planck itself. And this on the left shows the bias, the systematic error of these models in simulating rainfall over large-scale rainfall in summer. So blue means too much rain in the models compared to observations. Red means too little rain. Okay, so they have these errors. Now, on the right-hand side is the climate change signal of June, July, August precipitation from the late 21st century, from a CO2 scenario. The point I want to make here is that the signal that we're seeing from the models in terms of the climate change signal is actually, I was going to say, is the same size. It's typically the same size. In fact, it's, if anything, smaller than the systematic error or the bias. The scale is the same. So we've got a nonlinear system where the signal is comparable with the bias in the model. And as anyone who knows nonlinear systems, that's not a good state to be in. That's a situation where we can't rely on these predictions given these errors. Okay, so this is what a sort of kilometer scale atmosphere would look like with the convective systems in the tropics and the extratropical storms. This is what a kilometer system would look like in the ocean, and I refer to Andy Watson's talk this yesterday, where he talked about some of the problems in simulating decadal variations in carbon uptake. And you know, once you get down to kilometer scale, then you actually can resolve some of these eddies. These are different fields. We're looking at the sort of Gulf Stream region here, which are likely to be pretty important, I would suggest, in determining how the ocean uptakes carbon. So, you know, we're looking at a real quantum leap once we get down to these scales, both in the atmosphere and in the ocean. Okay, I just want to very briefly touch on something I started with about these nonlinear circulation regimes. And by the way, this links very much to a question that was raised in Thomas Stocker's presentation, because these nonlinear circulation regimes, you know, link to nonlinear structures. They link to the tipping points and the nonlinear structures that exist in the climate system. And the question was raised, well, you know, we see these nonlinear effects in very simple models. We see them in Lorentz's model, and we saw them in the sort of models that Thomas showed of a kind of tipping point behavior. And then the question is, well, we don't see them in more complex models, so maybe they don't exist. So here's some work I did a few years ago in a project called Athena, which actually made use of some of the biggest computers in the United States, funded by NSF, where we ran the ECMWF model at different resolutions. These are spectral resolutions, which don't really matter exactly what they are, except this one is at a climate type of resolution. This is the 150 kilometer type resolution. And this one here is a kind of an operational numerical weather prediction of around 20 kilometers at the time anyway. And this is a measure of the statistical significance of the regimes. The left-hand thing is from the observations. So these are circulation regimes which are highly significant according to our data. But you can see that the CMIT model on the right fails to reach a level of significance, whereas the numerical weather prediction resolution on the left gets quite close. It's actually, when you look in detail, you find actually it's not quite as good as the observations, but it's getting close to the observations. Why are the high resolutions so much better? There are two factors really. One is the better simulation of transient behavior and the interaction between transients and quasi-stationarity. The other one actually is just the topography, that you can better resolve the sharp features of places like Greenland or the Alps, you know, or the Rockies and so on. And probably our evidence at the moment suggests that actually, of the two, probably the better topography is the more important, but that's still an ongoing issue, I would say. But you know, I think the answer is low resolution climate models do a poor job at some of the key interactions which are important for maintaining quasi-stationary flows and therefore simulating these nonlinear structures. Whereas when we get towards high resolution, we do better. Okay, so can we afford, is exascale computing a possibility? Well, this is a slide or a picture I found from a Hewlett-Packard sort of publicity thing, which from a year or so ago, which says that, let's have a look now, in early 2023, Hewlett-Packard are going to deliver a exascale, so it's got 2 exaflops, that's 2 times 10 to the 18 floating point operations per second, in a machine called El Capitan. And it's going to be delivered to DOE's Lawrence Livermore National Laboratory. So that's all very good, except what is it going to be used for? it's going to enable advanced simulation and modeling to support the US nuclear stockpile and ensure its reliability and security. So I would say, look, we can produce these machines, or we certainly will in a year or so be producing and delivering these machines. Do we really have to only produce them for nuclear weapons simulations? I think these days climate change is arguably a much more important problem. And so I think there is a very good case for dedicated exascale computing as early as 2023 in climate. So for many years, I've been banging on about this. The people that know me will accuse me of being like a stuck record player. So this was from 10 years ago in Physics World, that we need something like a CERN for climate change, which will enable this type of dedicated exascale computing to be entirely devoted to the climate change problem. And CERN is a good example because CERN's been, very successful in finding the Higgs boson. I mean, people that don't know about the Higgs boson may not be impressed, but it's an important part of the Standard Model, and it's something that couldn't have been done by individual countries. It was by coming together that this particle was found. But actually, there's I think in our own field, or in my field, there's an even better example of what can be achieved if we pool human and computer resources. And it's a place I worked for many years, of which Italy, by the way, is a member state. And in fact, some of my best colleagues that I worked with over the years, like Stefano Tibaldi and Franco Molteni, Roberto Buizza, Laura Ferranti, and others, are working with the best Italian scientists at ECMWF, was one of my greatest pleasures. And I'm immensely proud of what we were able to achieve there. It's a supreme example of what can be achieved by pooling human resources and computer resources. It's from pretty much the first day it started in the 1970s. It's produced the single most successful and skillful forecasts out to 10 days, 2 weeks now ahead of any center in the world. And I would frequently get visits from United States agency managers asking what the secret of success was. And I said, it's very simple. It's because we can pool human and computer resources from many different countries. In the US, they tend to be very much kind of agency by agent, separate agencies for separate systems. And they don't have quite that level of pooling and international collaboration. So ECMWF, I think, is a fantastic example of what can be achieved. So I really want to kind of propose something like this in climate. So CERN, has dedicated hardware, it has dedicated intellectual resources, it brings together scientists from around the world. It has a budget of €1 billion roughly per year. I see a CERN for climate change, the equivalent of the Large Hadron Collider would be dedicated exascale computing. And it would also bring together scientists from around the world. This literally would have to be global. It's not, I don't think of the E of CERN really as just European, something which has global reach, to understand how extremes of climate are changing. And importantly, this would be a meeting ground between climate modelers and the various parts of the Earth system and societal systems that impact, where climate impacts, such as in economics, agronomists, health, hydrologists, urban planners, social scientists more generally. We'll be able to do serious calculations of the impacts of climate change at the regional level. And the ultimate objective is to make global society more resilient to the current extremes of climate that are happening. I think this is urgently needed in view of all of the extremes we've seen this year that clearly are going to be ongoing as climate change unfolds. And I'm very happy to see that this recommendation has been put to the as one of the key outcomes of our meeting this week. And I hope it goes to the Italian government, and that the Italian government can also liaise with the UK as we come to COP to ensure that a recommendation in this area really becomes part of the leaders' declaration at the end of COP, that they say we do need this to improve our ability to make global society more resilient. So I think I'll stop here and yeah, and maybe take questions or invite discussion. Thank you.
I'll repeat that because I wasn't on the mic. We have plenty of time for discussion. Who would like to ask a question? Yes, in the back.
Good morning. The modeling system, like you say, atmospheric cycle. It's, the weather events repeat themselves, but with changing or climate change, we are losing polar cell, and so they change the wave where the cells meet themselves, and they start to be bigger, and probably, I think, it will be 2 on the northern hemisphere. It will be in short time 2, became 2 from 3. This changed all the stuff, all the modeling system. So it started new chaotic periods probably in the weather system, and until also Antarctic will become only with 2 cells, until 3 like is now in the modeling system. And so I think you have to work in this chaotic changing, that make waves more bigger in the system, waves, latitude waves. I don't know if I explain myself, but I'm thinking at where the cells meet themselves, they make a waves, no? You know this, no? Okay, and this wave start to be bigger, and so we have the stream, more velocity, atmospheric velocity of mass of air, and we can see snow on the desert. Okay.
Excuse me, we
Yeah.
we don't have so much time. Can
Yeah,
you just get to the question? Yep, just
Sorry.
get to the question
I
itself.
finish.
Yeah.
That's no. I say you think that can be an explanation. You think that is the way, like you can see some new models, something like this as the question.
Well, look, I think, you know, what the process you describe is an interesting possibility, and you know, it's the sort of thing that can be seen in a simple model of climate. But you know, if we go to politicians, policymakers, and say, this is what's going to happen, you know, whatever the precise mechanism you're proposing, we better be confident that, you know, this really is going to happen. And just it coming out of a very idealized model is not enough evidence by itself to go to governments and say, this is what we got to prepare for. So that's my point, that we have to make sure our most sophisticated models also would simulate the effect that you're talking about. And I think at the moment, with the current generation of CMIT models, it's actually very difficult to be confident about the dynamical changes because of the sort of problems I mentioned with systematic errors and so on. So I accept the point you're making, that there are potential for big changes to the dynamics of the climate system, but we should avoid being alarmist just for the sake of being alarmist. We have to back up our ideas with rigorous science, and rigorous science demands reliable, accurate models, and that demands more investment in the science of climate modeling, in my view.
Okay. Yes, Andrew.
Hello, Tim. It's Andy Watson here. Thanks for a great talk. You described going to exascale computing, and that's clearly possible because they exist. But is this not, I mean, that really doesn't guarantee that you'll not really solve the problem of the parameterizations, because there doesn't appear to be a place where you ever solve that unless So is this not, in fact, I mean, after, let's suppose we get exascale computing, we would still not be able to be fully confident in our models, and we would probably want, yet bigger computers, which some of my colleagues tell me are actually at the moment just not even in principle possible.
Well, okay, so you're right to say that we will never solve the parameterization problem. There'll be still issues to do with how we represent cloud microphysics. We'll never get down to the scale of representing, cloud microphysics. But what we know is that the parameterizations which, certainly for circulation, are most important are the ones, principally the parameterization of deep convection, and perhaps secondarily the parameterization of the momentum deposition from things like orographic gravity waves. And in the oceans, you yourself, I think, made the point that some of the mesoscale eddy parameterizations are crucially important for how we simulate the oceans. So the more we can represent these by the laws of physics, rather than these rather heuristic formulae, I think the closer we are going to get to an answer that we feel more comfortable with and we feel is more reliable. You're right to say that it's not like we've completely solved the problem going in this direction, but this is, in my view, given the critical importance of this problem, this is an absolutely necessary step. And, by comparison with the money we spend on satellite programs and so on, and God knows, nuclear weapons, this is a small amount of money. So, it's a necessary thing to do. It doesn't completely solve the problem. Whether computers will get bigger or not, I don't know. I mean, I'm doing some work on quantum computing to solve nonlinear differential equations. It's not inconceivable in 20 years, quantum computers will have a role to play here. They won't completely take over, but they may have a role. I don't think we can tell. I mean, there are all sorts of interesting technologies to do with photonic computers. I could talk about this at length, actually, which I won't, which suggests we're nowhere near the limit of computational capability.
Okay, Thomas.
Thank you, Tim. This is Thomas. Thank you also for reminding us about these 5 messages that come out of this conference. You are absolutely to the point that these messages need to be transferred to the Italian government, who then brings it to COP26. I think it's one thing to have good discussions here in the room and write nice papers and good messages. If they are not put to the next level, it's futile. So thank you for that reminder. One point I wish to make, it seems to me that the observations also play a big role here for the success of a CERN for climate change. We've seen in recent years that, for example, precipitation observations are no longer sufficiently covering space so as to compare to the best CMIP6 models. Now, you are talking of an entirely new, much more highly resolved model generation. And if we don't have certain types of observations, we are basically in a void there to confront the new models with what is actually going on in the climate system. So this is one pitch for not forgetting the observations and the important interaction between modeling and observation, which I think is one ingredient of the success of ECMWF as well.
Yes, Thomas, I totally 100% agree with you, and I'm not in any way trying to set up a kind of a dichotomy between observations and modeling. You know, it's a false dichotomy. They're both clearly important. So I 100% accept what you say. I just want to re-emphasize, because I have had a bit of discussion. I am trying to kind of get the message also to the UK government about the need for this modeling development. And I just want to emphasize again, if we can get from the Academy to the Italian government, and if the Italian government can kind of push this onto the UK as well, I think between the UK and the Italian leadership, we have a chance of getting this really into the COP leaders' agenda. So I just stress again, for people who are thinking about the next steps after the end of this meeting, it's crucial to get these messages to the governments of Italy and the UK to make a success at COP.
I just quickly interject that having looked at NOAA's budget about 10 years ago, they were putting, I would say, 2 orders of magnitude more into satellite observations than to NWP. So at least then the balance was pretty skewed, just to put it in perspective. Do we have any questions from people online?
No questions.
Okay. Right. Well, maybe I will ask my own question, if I might be permitted to do that of you, Tim. I think you made very compelling arguments that we need to put much more investment into these sorts of models and try to get to the exascale. I don't disagree with that at all. But you use the European Center as, I think, a good example of what can come from cooperation, and yet forecasters all over the world are still glad that we have more than one modeling center. And they often look at this whole range of models, knowing perfectly well that on average one is inferior to another and so forth. So my question to you is pretty simple. Do you think optimally we need more than one CERN? Should we put all of our eggs in one basket, or should we have 2 or 3 or 4 around the world that are kind of competing and that give us a multi-model perspective, given the fact that, as Andrew quite correctly pointed out, we're never going to be able to do without some level of parameterization?
Okay, there are a number of issues. I think one point I want to make actually very clearly here is that I definitely do not see a model as a deterministic, a piece of deterministic code. So, you know, I've been pushing for a long time that models should be stochastic, and certainly the ECMWF model is stochastic. So the ECMWF model does actually, it's not like, you know, you say forecasters look at different models, but actually ECMWF is an ensemble of models, and the model equations themselves are perturbed with stochastic parameterizations. Whether the ECMWF ensemble is improved by including other models, we're getting slightly off topic here, Kerry, so I don't want to perhaps go down this route too much, but I think I'm not actually personally convinced that adding other models to the ECMWF ensemble necessarily improves their skill, but that's something we can discuss. But look, am I advocating one model? No, I'm not really. You know, in practice, there will be several. I mean, I envisage, you know, perhaps 1 or 2 per continent, and you know, we will in practice we will probably produce multi-model ensembles from a few kilometer scale models. But by a few, I mean, you know, let's say less than 10, not on the order of 100, which is what we have now in CMIP. The problem with CMIP is that individual institutes just don't have the critical mass of resources. So we end up with 100 rather poor models. I think having, you know, half a dozen or 10 good kilometer scale models is a much better route to go down. And we can explore some, I mean, this is obviously ongoing research in how you best represent model uncertainty. I'm certainly a believer that some level of stochasticity has to be added, even into these 1 kilometer models, to represent, as you say, things that are still parameterized and are uncertain. But yeah, I'm not in favor of one sort of monolithic model, and in practice that's never going to happen anyway. But some kind of rationalization so that we can develop a small number of kilometer scale models, I think that's vital.
Great, thank you. I have time for a quick question.
Just a comment. Tim, I'm Bruno Carli. About your request that the messages reach the COP26, I can assure you that at the opening of this conference, we had high-level representatives from the ministry that will provide the Italian delegation to the COP26. So our messages has reached the Italian delegation, and however, how much they will look at our message and how much they will be heard at the table of COP26, we don't know, but we have done our part.
I don't know whether there is I mean, in the UK, we have a specific person who is called the UK government chief scientist, and his name is Patrick Vallance. I don't know whether there is an equivalent position on the UK, Italian government of a sort of a Italian chief scientific officer or chief scientist. But if there is such a person, can I recommend that our message gets to that person, and then that person is encouraged to liaise with the UK chief scientist, Patrick Vallance, because then I think between them, they can craft a suitable statement which can go to the COP leaders.
That's an important point to take into account. Thank you.
Okay, well, I think we should give Tim another round of applause. Thank you very much, Tim. Our next speaker is Sami Solanki, who is a solar physicist and will talk to us about the possible contributions of the sun, variability of the sun to climate variability.
Yeah, ladies and gentlemen, honored chairman, it's a great honor for me to be here in these historic settings, and I hope I can tell you one or two words later on why it is particularly so. I put on a tie specifically for the talk so that you can see I'm an astronomer. There are stars on it, right? So I'm really an odd man out in this meeting here, and I'm very happy that you have given me a few minutes to say something about the sun and whether it contributes or to what extent it contributes to global warming. I would like to mention that Natalie Krivova, with whom I've done a lot of work, has given considerable help in putting together this presentation. So let's start with the sun. When you observe the sun, it looks like a boring ball at first sight, but if you look at it with better instrumentation, you find that it's a highly structured and extremely dynamic. So in the movie that's running on the lower left, in yellow, you see a part of the solar limb, the edge of the sun. You see structures above the limbs called spicules and prominences, and you see how dynamic it is. Things are moving there all the time. This is sort of the normal, everyday sun. Now, just like there are extreme weather and climate events, from time to time you also get extreme events on the sun, like what you're seeing in this upper right movie here. This is a so-called coronal mass ejection, which failed in this case. The material didn't quite make it out into interplanetary space. None of it came and hit the Earth. But it fell back on the sun and looks pretty spectacular, I find. Now, these are just some examples of many, many, many of what constitutes solar activity. And the nice thing is that all these active phenomena are finally driven by a single quantity, and that is the magnetic field of the sun. and how it interacts with the convection and the oscillations in the sun. So on the left, sorry, this movie stopped running. Let's see if it, no, it doesn't want to run again. Shows extrapolations of the magnetic field. It looks a little bit like the dipole of the Earth, but far more complex. And it's not just more complex, it's also very much more dynamic. That's what you're seeing in the movie that's running right now. In yellow and blue are the two opposite magnetic polarities of a so-called active region on the surface of the sun, as measured. The white lines or white curves connecting them are regions of particularly hot gas in the corona, in the atmosphere above it. And if you look at these loop-like structures on both sides, it will remind you a little bit like the classroom physics experiment of putting a bar magnet and strewing metal filings around it, except that in this case, the metal filings are jumping around all over the place because it's not static. It's a very complex and dynamic system. Now, solar activity and the magnetic field change on all time scales, from seconds to however long we could observe. But there is one particular time scale where we see a cycle, a very definite cycle, and that's around 11 years is the period. And to illustrate that, I'm showing you this figure, which is the sun taken in X-rays with one image taken per year. Starting in the beginning left, lower left, we have the sun at activity maximum. It's very bright in X-rays. As you go back every year, you can see that it gets less and less bright. And about 5-6 years later, you have a sun which has 1% of the X-ray brightness that it had at its activity. You wait another 4 or 5 years and it's back again. And this keeps going up and down time again. Now in X-rays, as I said, it's a huge change in brightness. If we now integrate the radiation coming from the whole solar disk over all wavelengths to get what is called total solar irradiance, which is basically all the energy that's coming from outside the Earth system onto the Earth, that varies also, but by a much smaller amount. Now, because the sun is giving all the external, or 99.9 whatever % of the input to the climate system from outside the Earth, obviously it is what determines climate on Earth. If the sun were not shining, we would be in deep trouble. The atmosphere would cool relatively rapidly, and at some point would be cold enough that nitrogen would become liquid and we would lose most of our atmosphere, and life on the surface of the Earth would become, let's say, difficult. Okay? Now, that's a different thing from does the sun affect climate change? And it depends on the time scales, right? On very long time scales, sure, because the sun evolves and at some point it's going to win and it's going to get rather warm on Earth. But what about on time scales like decades, centuries? And so we have measurements going back a bit more than 40 years of the variations that are sufficiently accurate to determine the variations of the brightness of the sun, of the total irradiance. And this is such a data set plotted here. The actual measurements are in color. Looks very noisy. If you look at the black line, the thick black line, that's a smooth curve of this. And there you can see the cycles. You can see that there are times in this 11 years where the sun is bright and where it is less bright. Now the noise is not because the measurements are no good, it's intrinsically solar. If you look at one of these dips, it's asymmetric. You have a lot of dips where the sun darkens for a short period of time. If you look at a blow up of one of these dips, you see that they are produced when you have dark sunspots, so dark features on the sun, and they move over the solar disk because the sun rotates. And whenever there are dark features on the sunspot, there is less radiation coming out of the sun, and the sun as a whole gets a little bit darker. However, these variations are on the order of 0.1%, not 2 orders of magnitude as for the X-rays, right, if you take the whole thing. Now, allow me one extra slide that I had to build in, because we are here in a historic place, and Galilei was one of the early Lincei, and he was probably one of the co-discoverers of sunspots. It's not quite clear. There were 4 different people or groups that claimed to have discovered them, and they did it more or less independently. So let's say he was a co-discoverer. He was not the first to publish, though. But he was the one, although his observations were less sparse than those of, let's say, Christoph Scheiner, who observed very, very carefully for many years. He was a brilliant scientist, and he got a lot of results out of them. He got a lot of insight out of these relatively few observations. So this is a movie put together from observations that Galilei made, from his sketches of the sunspots. And he didn't have computers to play the movie, but he could do it in his mind, and he said, yep, these things move across the sun as if the sun were a rotating sphere. So he did the correct geometrical interpretation for that. He noticed that sunspots appear, disappear, they evolve in between, and he used this as an argument to say, no, the current theory for sunspots is not correct, which had been put together by other people, that they are planets orbiting the sun, because that's the only thing one could think of, and they're crossing the solar disk. He said, no, no, no. These have to be features on the sun, which was heresy, of course, because that, maculae, the sun was not a perfect sphere as it should have been. And he noticed, and this is quite remarkable, because sunspots look really black, and he noticed that they are not actually black. They're quite bright. He said, if you take a sunspot and put it on the night sky, it will be brighter than most of the stars. It only appears dark because it's less bright than the surrounding photosphere of the sun. So very insightful. Okay, so sunspots. Absolutely important for irradiance, as we noticed. However, there's a bit of a conundrum. If you look at these 2 figures, the upper one shows again the irradiance. Now, this is smooth over 81 days or something, and so that you see the cycle very nicely. And below that, I've plotted the number of sunspots, also smooth over the same period of time. And lo and behold, the sun is actually brighter when you have more sunspots. Although I just showed to you that the sun gets dark when you have dark sunspots. So this is not quite logical, is it? I think it just means we are missing something. Right? And what we are missing are so-called faculae. And here is a picture of a small part of the solar surface where you have 2 small sunspots. These are the dark guys. You have a lot of convective features, which is sort of the gray stuff in the middle. And then you have a lot and a lot and a lot of little bright guys. Little means a few hundred kilometers in size, right? The sun is big. It's 1.5 million kilometers in diameter. And these little bright guys called faculae, each of them is not much relative to sunspot, but there are many more of them. Factor of 10 to 100 to 1,000. And as we go through the solar cycle and the number of sunspots increases, the faculae also, their coverage increases by an even larger factor, and they dominate. So on the short time scales, the sunspots lead to a darkening, but on the longer time scales, the little faculae win. Right? Okay. Using this, and both of these, both the sunspots and the faculae, are places where you have strong concentrated magnetic fields. So if you take the assumption that the magnetic fields at the surface of the sun are causing total irradiance, you can then build a model, which various people have done, but I think we did it with the most physics in it, and you can compute the irradiance change, and you can compare that with what has been measured. And they agree pretty well. This is one way of showing that. This is another way. This is now a wavelet power spectrum, which is something like a Fourier power spectrum, not quite so highly resolved in frequency. And there are two curves on here. One is observations of irradiance over 20 years, and the other is the model, the satire model that we have computed irradiance over the same period of time, and they agree remarkably well over 6 orders of magnitude in frequency and 8 orders of magnitude in power. So it shows that we got something right. And from this diagram, you can also work out quite easily what different kinds of features are doing. So you see a peak at around 11 years. That's your 11-year cycle. That's where you have the most power. All the longer time scales are dominated by the faculae. There should be a peak at 27 days, which is the solar rotation period. It's not well visible. That's dominated by sunspots. It's not well visible because sunspots don't live long enough. They don't keep coming back. You don't see a periodic signal. And then at the very short end, you have the convective cells, the granulation, which is dominating. So we seem to have got most of the things right there, and we can then use this information to compute irradiance on longer time scales. Then you can measure it, because the measurements are restricted to the space age starting in 1978. What are the data we have to go further back in time? We will need some kind of data, because we cannot a priori, starting from just from scratch, compute what solar activity did on a certain period or day. We can also not make any predictions about that. So direct observations, the longest running data set we have, is just simple counts of sunspots. So many sunspots on the solar disk. This was easy to do even with a very simple telescope, and this started in 1610, is ongoing till now. This is one such data set. There are different ways of scaling, etc. This is just one of them. And there are a couple of things you notice. The first is that the 11-year cycle is extremely prominent in sunspots. The second thing is it's a cycle. It's not a periodicity. You have strong cycles, you have very weak cycles, and there was a period in the second half of the 17th century where over 60 years there were basically no sunspots whatsoever. This is called the Maunder minimum. Also, the length of the cycle varies, the shape varies, etc. Now, whether by chance or not, the Maunder minimum happened to coincide with a particularly cold part of the Little Ice Age. There is another period here in the direct telescopic record where you had very low solar activity called the Dalton minimum. This turned out to be a particularly cold period again, especially in England. Again, I think I've forgotten, sorry. One of the speakers pointed out that, the Little Ice Age was a more European thing. It was Thomas Schocker, right? Was a more European thing and not equally seen all over the world. That's a caveat we'll put in there. However, it turns out even these 400 years to see any kind of proper correlation with climate is much too short. And we need a much longer time scale. Before the telescope, direct observations become difficult. There are naked eye observations of sunspots, but they are very irregular. But luckily, nature is kind to us. It has provided us with multiple records that we can use to deduce solar activity over longer periods of time. And all of these have in common that these are cosmogenic isotopes. The solar system is being bombarded by high-energy particles, galactic cosmic rays, coming either from the galaxy or even from further away, the highest energies, all the time. Some of these particles, these are usually protons traveling at close to the speed of light, reach the inner solar system. Some of them will reach the Earth. They will not get very far usually before they will interact with one of the constituents of the Earth's atmosphere. Usually it will be nitrogen, because that's the most common. And when they interact, these are nuclear reactions. complex nuclear reactions. One of these showers is shown on the image on the right. And they will change the constituent of the atmosphere. For example, producing, instead of 14 nitrogen, 14 carbon, which is radioactive. That means any carbon-14 that had been there when the Earth was formed would have long ago gone, because it has a half-life of less than 6,000 years. That's why we can use it so well for radiocarbon dating. Most of this, as we also heard very nicely earlier in the talk, in the very first talk actually, gets dumped into the ocean. Some of it is taken up by trees and stored within the tree trunks. And if we can now measure the age through the tree rings, through dendrochronology, we can say exactly how much carbon-14 was formed at a particular time. Now, what does that have to do with solar activity? If the sun is more active and has a stronger magnetic field, this magnetic field acts as a shield. So when the field is strong, few galactic cosmic rays reach the Earth. Less carbon-14 or beryllium-10 or whatever is formed and stored. So if we can work out what the formation rate was, we can determine how active the sun was, how strong its magnetic field was. And using that and a set of models, we can go back and reconstruct, for example, the sunspot number over the Holocene. We can't go further back than that because there are assumptions about what the oceans have been doing, etc. And all this changes when you get into the Younger Dryas or the last glacial. If you look at this record, this is not the most recent one, but it's sort of a nicer drawing than we had in the most recent paper. You see a couple of things. This is all averaged over 20, 30 years. You don't see the cycle anymore. You don't see that in carbon. Well, in the most recent measurements you do, but in these earlier ones you didn't. But what you see is, if you look at this, let me use the pointer so that the online people can see as well. You see these little blue marked things down here? The last one of these is the Maunder minimum. Very low solar activity. Basically no sunspots. But oops, now what happens? I'm getting, if I touch it, that's not good. There were earlier such grand minima, going further back in time. Most of the time the sun spent at an intermediate level of activity, but there were also times when the sun was particularly active, and the second half of the 20th century was actually one of these grand maxima, when the sun was very active. This has been changing in the last 20, 30 years. Solar activity has been decreasing again, and I would say now we are back in a normal phase of activity where the sun has spent most of its time. This last grand maximum was one of the longer ones, has in the meantime ended. Okay, so now once we have such a long time series, we can perhaps go and, or different people have done this, go and compare with various measures of what climate looks like. And various people have done that. Gerald Bond compared with ice-rafted debris in the North Atlantic. There has been work on the Alaskan subarctic and lakes in southern Alaska, and caves in Oman, etc. And in all these cases, you find on these very long time scales that there is a correlation between solar activity and climate. So these natural climate variations, to some extent, the sun seems to have had an effect. But again, I would say this is a correlation. Correlation does not mean causation. Okay? But there is some evidence for that. Now, when we come to the more recent time, and this is going to be a total change in scale, in time scale, you find that up to the middle end of the 20th century, there still was maybe some kind of correlation. But the last 3 decades or so, this has broken down. In red is one particular reconstruction of temperature, the GIST temp 3.1. In yellow is one particular reconstruction set of measurements for irradiance. And you can see till about 1990, they have fluctuations, but are not terribly different. After that, they are totally different. There are obviously uncertainties. There are bigger uncertainties in the irradiance than in the temperature. Temperature is a little bit easier to measure than irradiance, although there are tricks that one has to do there as well. So I would add this triangle to say that's sort of the range of uncertainties where we have for the irradiance over the last 30 years. But I think it's going to be very difficult to argue that irradiance has been increasing. Wouldn't make sense either, because activity has been going down. Yeah? Okay. Now, as I mentioned, correlation is not causation. It doesn't just depend on whether the 2 curves look similar. It also depends what is the magnitude of change of irradiance. We have seen that over the solar cycle, that's what's measured, we have about 1 watt per square meter. On longer time scales, it becomes more difficult because you're dependent on models and you put in different assumptions, and it turns out the models gave you vastly different results. Anywhere between 0.6 watt per square meter or even less, up to 6 watts per square meter, a whole order of magnitude. And that, I think, is a highly unsatisfactory situation, because this difference basically means either you have a sun with a very strong forcing of climate or a sun with extremely weak forcing of climate. This is not terribly satisfactory. Now, there has been very recent work by Yeo et al., who used a totally independent technique and has strengthened the case for the small forcing with setting an upper limit of 2.7 watts per square meter. But still, I think there is still a lot of work to be done there. The reason for the uncertainty is that all these models going back in time, they only have the sunspot number to rely on for if you go far back in time. And that's not sufficient, because the sunspot number only tracks the sunspots, and you have to somehow imagine what the faculae have been doing or make some assumptions about that. And different assumptions give you different results. We hope this will change. We have been working very hard in the last few years with Theo Hatzistergos to calibrate and correct historic observations of the sun, images taken in calcium, in a calcium spectral line, which shows the faculae very, very well over the whole solar disk. And this is work for the next few years to then do a better reconstruction and fix this problem, hopefully.
5 minutes.
Okay. All right, that's very good that I only have 5 minutes, because now I'm coming to the part where, this is not my field. I'm an astronomer, solar physicist. This is coming to Earth climate. And so I'll go very fast over that. Another uncertainty from the Earth's climate side is, how does the sun affect the climate? In what sense? What are the effects taking place within the atmosphere? And there are 2 basic schools. One is the bottom-up, which says it's mainly the total irradiance in the visible, infrared, whatever. That's radiation that gets down to the ground if there are no clouds, gets absorbed, reflected, re-emitted, whatever, and enters the Earth system that way. This is what GCMs have. There have been some discussion about the sensitivity to that. GCMs give different results than if you compare directly with temperature measurements. There's a new paper which claims that it can get over this difference. The other pathway is top-down, where you get, this is the UV radiation of the sun, which is decisive. That gets absorbed directly in the upper atmosphere or in the stratosphere or higher up. That's a much more complex pathway. Relatively few GCMs have this already incorporated, but the newest generation is doing that more and more. And so it could also be that some of the differences in the sensitivity have to do with that, that they're not incorporating the top-down mechanism. On the solar side, there are problems there with the UV irradiance as well. The variability is not very well known. It could be anywhere between 20% and 120% of the total, of the variability of TSI, of the total energy change. It can be more than 120% because according to these measurements, the visible light goes in the opposite direction. The models and the data don't agree with each other. Different models don't agree with each other. There's a lot of work to be done there as well. But the UV is interesting because it changes a lot compared to TSI. All right. So after having glibly jumped over these parts, I come to my conclusions, if I may. I have divided them into 3 parts. There is a green, yellow, and red part. The green part is, I think, something that most people in the community will agree. Yellow part is where there is disagreement, but I think we are on a path to resolve that. And red is something where we really need more work, or a lot more work to be done. So, first of all, the sun, also sends energetic particles to the Earth and so on. Their effect is probably small. The main driver for climate is brightness change, irradiance change of the sun, both total, integrated over the whole spectrum, or in a certain spectral range, in the UV mainly. The irradiance itself is changed by the magnetic field, oops, I have to be careful, by the magnetic field at the solar surface in the form of spots and faculae. Solar activity correlates with various measures of climate on long time scales in the sense of over the Holocene. This correlation has broken down in recent decades, and the total solar irradiance has not followed the rapid rise in temperature in the last 3 decades. There is strong disagreement between the models on the magnitude of the rise of irradiance since the Maunder minimum, but there is a probability that it's not going to be too high, that it's more on the lower end, which would restrict the amount that the sun could have changed on irradiance. You find different sensitivity to changes in the irradiance of the temperature, depending on whether you use temperature measurements or what you get from GCMs. And that's a factor of around 3 or 4. However, recent result seems to support the lower values. There is still discussion about bottom-up versus the top-down mechanism, which one is the dominant one. For the top-down, you need to have reliable values of the UV irradiance. There we are really got a big disagreement between 30% and 120%. But there will be a new Indian satellite, Aditya, flying next year, which hopefully will help us to resolve this. And one thing I didn't mention very much that would go too far, at the moment, solar physics is not really a true science because we cannot predict. We cannot predict what solar activity will be, neither tomorrow nor next year, and certainly not in 50 or 100 years. Thank you very much for your attention.
Could I begin by asking you, I think, a simple question? I seem to recall that at one period in the history of this research, there was a suggestion that you could alter weather, particularly clouds, directly through the cosmic ray modulation. You didn't mention that. Has that now been sort of disproven?
Yeah, so the cosmic ray effect, this was a Danish group that had a number of papers on correlations between cosmic rays reaching the upper atmosphere and cloudiness. And there was a lot of controversy about that, going to the extent of people saying that they had been shifting satellite data, because the cloud coverage had been measured by different satellites, and satellites don't live forever, and you have to recalibrate it, and the people who built the instruments didn't agree with the way they had recalibrated them. Also, there was an experiment at CERN called CLOUD, which looked for the effect in a cloud chamber of shooting in cosmic rays, that means high energy particles coming from the SPS source in CERN, and seeing how well it would seed these clouds. And they found lots of interesting physics on aerosols and all kinds of things, but they couldn't actually reproduce the level of cloudiness to be produced for this effect to be important.
Okay. All right, so the floor is open for questions. Anyone? Yes, Thomas.
Thanks very much, Sami, for this interesting talk. I didn't quite understand that top-down mechanism. If you could say a few more words, what exactly is that doing? I saw lots of feedbacks, but I didn't really grasp it. Thank you.
Let me do it in a very basic level, because as I said, I'm not an atmospheric physicist. This is a plot of the altitude at which solar radiation at different wavelengths gets absorbed in the atmosphere. Right? So starting at 0, which would be gamma rays almost, and going on, this is in nanometers, so we are in the UV over most of this. And you see, as you go to short wavelengths, the absorption happens very, very high in the atmosphere. And these are different molecules that are playing a role there at these different altitudes. And most of this happens in the stratosphere, in the mesosphere, and the thermosphere. At the very short wavelength, very high up, it's oxygen, nitrogen, single oxygen atoms. But this is so high up that it's unlikely to have a large effect on the troposphere. So the interesting part is this here. This is wavelengths between 2 and around 400 or 300 something nanometers. And there, the two molecules which are driving this whole thing are oxygen and ozone. And at the longer wavelengths, solar radiation will break up the ozone molecule and produce oxygen, and will be absorbed in the process. At the shorter wavelength, the oxygen molecule will be broken up because it needs more energy to do that. It's more tightly bound than ozone is, and so the short wavelengths can do that. Again, that photon will be absorbed, and so you get all the energy basically directly absorbed in the stratosphere. And then all the complicated stuff, and I have to admit I'm not very strong on that, all this complicated stuff then comes from how do you get the energy from, which has now been absorbed and heated the stratosphere, down into the troposphere. And that's where Walker and Hadley cells, et cetera, and all these things come in. And I'm not a specialist, so I'm not going to burn my fingers and try and explain that.
Thank you.
I'm a little bit more of a specialist, I guess. I don't understand how you could do that. Are there any further questions? Are there questions from outside?
Yes. Sami, there is a quite long question from Nicola Scaffetta.
Mm-hmm.
The satellite total solar irradiance record since 1978 is highly controversial because the Accademia JPL NASA science team, which has collected most of the used TSI data, claims that the TSI has increased from 98 to 2000 and slightly decreased afterward, while the PMOD Switzerland science team, which is the only TSI record that you have shown, claims a continuous slight decrease, as seen in the sunspot number record. However, the PMOD TSI reconstruction is based on crucial modifications of the experimental satellite data produced by Accademia and by the Nimbus 7 Herb measurements. modifications that the experimental team rejected because not experimentally justified. Thus, is it not possible that your proposed TSI proxy model and relative climatic interpretation are wrong because they will not fit the Accademia TSI composite that would imply a warming from 97 to 2000? Any comment?
Right, okay. Not entirely surprising. So thank you very much for that question. It's very good, and it highlights a problem that there is with TSI, and I made this slide. I didn't want to show it in the main talk because it takes some time. And there was too much other stuff that I found more interesting that I wanted to show you. So these are the actual measurements, right? And you see there have been a whole bunch of them. Each of these curves was taken by a different instrument on a different satellite. Satellites don't live forever, instruments don't live forever. And especially the early ones, as you can see, they were wrong in absolute value as well, or they were different. Yeah? So there was a lot of scatter. In recent years, with better calibrations on ground, the scatter has more or less disappeared. So also in absolute value, they're much closer to, they're not exactly the same, but they're much closer to each other. They show similar, not exactly the same, but they show similar variation, but the absolute value is different. Now, if you want to make one record out of this, you have to somehow shift them to each other. There has also been, and this is what he meant here in the very early dates, etc., and there was a time when there was an outage here in the ERB experiment, which is really a critical one, because it was the one that started earliest, but also maybe not so well done as later ones. And whether one corrects for this or doesn't correct for this, you get different levels of the minima of the first and second minima that you have. And this is the problem that he is pointing out. Various people have put together these data sets, right? And this is a very recent one done by Greg Kopp. And they all get slightly different results. And the main difference, however, is in these very early times. And there is one that is the Accademia composite, which actually shows the second minimum is a bit higher than the first one. But then afterwards, it goes down again. Others are completely flat, more or less, and others are actually going down. And this was the reason, if you forgive me, I will go up. Now, how do I do that? This was the reason I introduced this triangle over here. To say that there is an uncertainty, right? This is using the PMOD composite, and there it shows there is a clear downward trend. That may be so. It has a certain logic to it because solar activity has been going down, and the models show the same. On the other hand, there are other composites which do not show that. But even the Accademia composite doesn't show that it's going up, up, up like the temperature curve.
Two more questions. Sami, two more questions. One from Gianluca Limonti. IPCC rules out any sun influence on climate while you leave a big window open, considering the big TSI uncertainty. May you comment on this?
Well, I don't know if it's a big window. As I said, the correlation has broken down, and these temperature variations we had during the Holocene were tiny compared to the temperature increase during the 20th and 21st century. I don't remember who showed such a graph earlier. Forgive me, I'm just, I'm mixing up talks. But we had this graph of or maybe it was Thomas again, of the temperature, the hockey stick kind of thing, slowly dropping and then shooting up really high. Fluctuations at earlier times were much smaller. also these comparisons are with local fluctuation. That doesn't mean that global temperature changed that much at that time. So yes, the sun probably had an effect. I think it's unlikely it is having a big effect now. And there have been, in the last 5-6 years, there have been a whole bunch of papers where people assumed taking moderate to intermediate differences in the irradiance between a Maunder minimum kind of state, a grand minimum, and a current state of activity. And they said, what happens if we have another grand minimum in 20 years from now? Yeah. You cannot rule it out. We cannot predict. And they showed that it will just maybe slow down global warming a little bit, but it's not going to stop it. And you will see, 0.1 degree or even less change. But if it were a very strong forcing, yes, then the sun could have a bigger effect. But I don't think that's very likely. I just say it's an uncertainty that is there.
You say you have one more question?
Yeah, one
Okay,
more
let's
from
hold it to
Timmy,
that.
remote.
Yep.
First of all, just an extremely interesting and clear talk. I appreciate it very much. I had a couple of, they're more comments actually than questions. The first comment was, I believe it's the case that during the Maunder minimum and the other minimum you mentioned, there was a considerable amount of volcanic activity, and I believe the modelers are more confident that that is likely to be an explanation of the regional cold event than the sun directly. So, but at least volcanism is a kind of confounding factor here in trying to assess causality. The second point I wanted to make was about the top-down mechanism, because I was sort of involved in a paper I was a bit critical of actually from the UK Met Office that claimed that there was an impact of the 11-year solar cycle on the surface climate. And what they did was they forced the model with the solar data from source, but it was the one which had the very high level of UV variability.
Yes.
And indeed it did produce, the model produced quite a strong top-down effect of changing, forcing the ozone. That made there was a temperature signal in the upper stratosphere. And that in turn led to a kind of downward propagation of zonal mean winds in the stratosphere, which then reached the tropopause and started to affect the tropospheric dynamics. Now, my argument was that if this was realistic, if the UV forcing was realistic and the model was realistic, then we should also be able to see this downward propagation on an 11-year timescale of the zonal mean winds, because that was a part of the top-down mechanism. But when you look at the reanalysis data, you don't see any evidence of such a clear 11-year downward propagation in zonal winds. So I think comparing the model response in the mid to lower stratosphere with the observations, meteorological observations of wind, is actually an indirect way of ruling out that high level of UV variance or forcing associated with the solar cycle. So in my view, I think that there is a potential top-down mechanism, but I think the evidence is that the enhanced UV forcing is unrealistic because it's producing an unrealistically strong meteorological response in the stratosphere.
Yeah, thank you for both these comments. I think they're very insightful. Firstly, I apologize. I wanted to say something about the volcanoes and then I forgot in the heat of the moment. That's absolutely correct, that for the Maunder minimum, you had strong volcanic activity higher than you had before, and that for many modelers, that appears to be a driver. For the top-down mechanism, I appreciate that comment. I wasn't aware of this work. And I think that's very nice because I personally also think that the source very high UV variability is much too high, but that's because we made one of the models which shows a much smaller variation. Still, as a solar physicist, I would prefer not to have a climate model tell us that this is what's happening, but have a direct measurement. And that's where there is an instrument, that's a suit instrument for solar UV imaging telescope that will fly next year, where we hope to be able to get this, to nail this down, how big this will be. But thank you for the comments. Very, very good.
Well, I think we should thank the speaker again. Very interesting, enlightening talk. Yes.